When NASA's New Horizons spacecraft flew past Pluto in 2015, it gave us something we'd never had before. A close-up view of a world that had only been a blurry dot for decades. What it revealed was stunning. This distant dwarf planet, once thought to be lifeless and dull, turned out to be surprisingly dynamic. We saw vast glaciers made of nitrogen, towering mountains built from water ice, and a thin bluish haze that formed an atmosphere glowing faintly in sunlight. However, as beautiful as it looked, something didn't add up. That hazy atmosphere was far colder than scientists had predicted. According to existing models, Pluto's atmosphere should have been much warmer. But something strange was cooling it far more efficiently than expected. But what? For years, researchers searched for answers, comparing data and refining their models. Then, in 2017, a new idea emerged, one that seemed almost too strange to be true. There was no way to test it at the time, but in 2021, the launch of the James Webb Space Telescope changed that. With its powerful infrared eyes, Webb was finally able to study Pluto's atmosphere in detail. And it confirmed what was once termed a crazy idea about Pluto, solving a decade-long mystery surrounding the dwarf planet. So, what exactly is happening on Pluto? To answer that, let's rewind a bit. And before we begin, don't forget to subscribe to our channel so you never miss a single update from the universe. For most of the 20th century, Pluto remained one of the greatest mysteries of our solar system. More than 5 billion kilometers from the Sun, it appeared through telescopes as nothing more than a faint, flickering dot. Astronomers knew it was small and icy, about 2/3 the size of our Moon. And they suspected it might have a thin atmosphere, one that could possibly freeze and vanish as Pluto moved farther from the Sun during its long orbit. But beyond these vague ideas, no one really knew what Pluto was like. There was no data, only guesses. That's why NASA's New Horizons mission was so critical. Time was running out. Scientists feared that if the spacecraft wasn't launched by 2006, it wouldn't reach Pluto before its atmosphere froze and collapsed onto the surface due to the planet's distance from the Sun. If that happened, we could lose our only chance to study Pluto's atmosphere up close, possibly for centuries. The mission had to make it within a very narrow window. New Horizons launched right on schedule in January 2006. After a 9-year journey across the solar system, it finally reached Pluto in July 2015, and what it discovered stunned the world. Pluto wasn't a cold, dead rock. It was alive with activity. Towering mountains made of solid water ice bulged into the sky. Vast glaciers of nitrogen and methane flowed across the surface. But perhaps the most unexpected discovery was above it all, a fragile, layered atmosphere. It wasn't thick, but it was there, rising more than 300 kilometers above the surface. Made mostly of nitrogen, with traces of methane and carbon monoxide, Pluto's atmosphere glowed with layers of haze, dozens of separate haze layers stacked up into the sky, each scattering sunlight and giving the atmosphere a bluish glow. But how does Pluto's strange bluish haze actually form? It turns out this process begins high in the atmosphere with an unlikely ingredient, sunlight. Even though Pluto is incredibly far from the Sun, so far that sunlight is 1,000 times weaker than on Earth, ultraviolet rays still reach it. These rays have just enough energy to break apart methane molecules in Pluto's atmosphere. This is the first step. When a methane molecule gets hit by UV light, it splits into a methyl radical and a hydrogen atom. In the second step, these broken fragments don't just float away. They start reacting and sticking together, forming more complex hydrocarbons like ethane, ethylene, and acetylene, slightly heavier and more stable than methane. Then comes the final step. These molecules keep combining and growing into even larger, more complex compounds, eventually forming solid tar-like particles called tholins. These are not gases anymore. They're tiny solid bits of organic matter. As they slowly drift downward through Pluto's thin atmosphere, they begin to gather and form distinct layers of haze. These layers scatter sunlight, giving the sky a soft bluish glow, something New Horizons was lucky enough to capture. Unlike the haze on Earth, which mostly comes from moisture, dust, or pollution near the surface, Pluto's haze is born from chemistry happening high above. It's more like what we see on Titan, Saturn's largest moon. But on Pluto, this haze turned out to be more than just a beautiful feature. It was a clue to a much deeper mystery. Why is this haze so important? Because something about Pluto's atmosphere didn't make sense. Before New Horizons arrived, scientists had created models to estimate what Pluto's upper atmosphere should be like. Since its atmosphere is made mostly of nitrogen, with traces of methane and carbon monoxide, the models predicted a temperature of around 100 Kelvin. That's about negative 173 degrees Celsius or negative 280 degrees Fahrenheit. Cold, yes, but still within expectations for a planet that far from the Sun. But when New Horizons actually flew past Pluto and took direct measurements, the results were shocking. Pluto's atmosphere wasn't 100 Kelvin. It was much colder. In fact, it was closer to 65 or 70 Kelvin, a difference of over 30 degrees. For planetary scientists, that was a huge gap. It meant that something was cooling the atmosphere far more efficiently than anyone had expected. To solve the mystery of Pluto's unusually cold atmosphere, scientists began to look more closely at the haze itself. And in 2017, a planetary scientist named Shi Zheng from UC Santa Cruz proposed a bold and unconventional idea. Pluto defied our models because something was quietly scattering the light, hiding the truth in plain sight. Here on Earth, our view of the world can be just as distorted, not by particles, but by headlines, bias, and algorithmic filters. Most of us only see a narrow slice of reality shaped by the outlets we follow and the region we live in. And when it comes to science news, it gets even trickier. Headlines are often exaggerated or oversimplified to get clicks. That's why I use Ground News. It's a platform that helps you cut through bias and hype by comparing how different media outlets are covering the same story. It shows you political slant, headline framing, and even what stories you might be missing entirely. For example, when this new discovery broke, I used Ground News to ensure I was reading balanced, credible coverage. I could instantly check each outlet's factuality rating, which is verified by 3 independent organizations. For every story, they also show the bias distribution, ownership, and where each report source is located. And here's something cool. The founder of Ground News is a former NASA engineer, so you'll find a strong foundation for trustworthy science coverage too. My favorite feature? The blind spot. It highlights stories that are disproportionately covered by one side of the political spectrum, so you're always aware of what your feed might be leaving out. If you're only interested in topics like science, the interest pages filter out the noise and show you only what matters to you. There's a special offer for viewers of this channel. For a limited time, you can subscribe and get 40% off the Unlimited Access Vantage plan by scanning this QR code on screen or heading to ground.news/SOU. The link is also in the description. Now back to space. Scientists began to look more closely at the haze itself. And in 2017, a planetary scientist named Shi Zheng from UC Santa Cruz proposed a bold and unconventional idea. What if the haze wasn't just a passive feature floating in Pluto's skies? What if it were actively controlling the planet's temperature? Zheng suggested that these tiny haze particles could be absorbing sunlight and then re-emitting that energy as heat, not invisible light, but as mid-infrared radiation. On Pluto, where the atmosphere is incredibly thin and packed with these haze particles, this process could be powerful enough to cool the entire atmosphere far more efficiently than gases alone ever could. It was a radical idea. Until then, scientists had always believed that atmospheric temperature was mostly controlled by gases, like carbon dioxide on Earth or methane on Titan. The notion that solid particles could dominate this process seemed strange and hard to accept. If Pluto's haze was indeed cooling the atmosphere, then it should emit a specific signal in the mid-infrared, a wavelength that only a very sensitive telescope could detect. Unfortunately, at the time, no telescope on Earth or in orbit had the precision to detect such a faint signal. Pluto is tiny, distant, and sits close to its large moon, Charon, making it even harder to isolate emissions from just Pluto's atmosphere. But all of that was about to change. In 2021, a new chapter in space exploration began with the launch of the James Webb Space Telescope. With its massive 6.5-meter mirror and cutting-edge infrared instruments, Webb was built to peer into the coldest and faintest corners of the universe, making it the perfect tool to test Young's bold theory about Pluto. One instrument on board was especially important: the Mid-Infrared Instrument, or MIRI. This device can detect light in the 4.9 to 27 micron range, exactly the part of the spectrum where Pluto's haze particles would emit heat if they were, in fact, cooling the atmosphere as Zhang had proposed. Then, in May 2023, the moment finally arrived. An international team of scientists pointed the James Webb Space Telescope toward Pluto and its moon Charon. For the first time ever, scientists could clearly separate the two worlds in infrared light. This was a huge breakthrough. Earlier telescopes had always blurred the distinction between Pluto and Charon, making it impossible to determine which heat was coming from which body. But Webb's powerful infrared vision changed that. It allowed researchers to cleanly isolate the thermal glow of each object, something no one had been able to do before. One figure in the results shows exactly how Webb achieved this. The black dots represent the thermal emission Webb measured from the region. The smooth blue and red lines are model curves used to match Charon's thermal signature. Once they had a precise model of Charon's heat, they could subtract it, leaving behind a clear picture of Pluto's own mid-infrared emission. When scientists examined Pluto's thermal emission using JWST, they spotted something unexpected. The infrared glow coming from Pluto was stronger than what its icy surface alone could produce. That meant something else. Something above the surface was radiating heat. This became even more obvious when the team looked at the data in detail. Have a look at this figure from the research paper. It shows how much heat Pluto is emitting at 4 different infrared wavelengths: 15, 18, 21, and 25 microns, as seen by Webb. The main goal? To figure out how much of this heat is coming from Pluto's icy surface and how much is coming from its hazy atmosphere. Each column in the figure represents a different wavelength. Things get especially interesting in the bottom row of the figure. These plots show the absolute amount of heat Pluto is radiating into space, as measured by JWST. The black dots are the actual observations, real data points showing how much infrared energy Pluto emits at each wavelength. The purple line represents the energy from sunlight that reflects off Pluto's icy surface, essentially the visible light that bounces back into space. The cyan line shows the heat being emitted by Pluto's thin atmosphere, including both gases and the tiny haze particles suspended in the air. Finally, the gray line at the top combines all these sources to give the total calculated heat emission from Pluto. And here's the key point. The gray line matches the black data points remarkably well. That near-perfect fit confirms something groundbreaking. Pluto's haze isn't just floating in the background, it's glowing in the infrared and actively radiating heat, playing a major role in cooling the atmosphere. What was once just a speculative idea is now backed by hard evidence. But why does any of this matter? Why is Pluto's haze such a big deal? Well, on most planets, like Earth, Mars, or Venus, it's the atmospheric gases that do the heavy lifting when it comes to climate. They absorb sunlight, trap heat, and radiate energy back into space. Tiny solid particles like dust or haze might contribute a little, but they've never been the main driver. Pluto changes that. For the first time, we see a world where the haze, not the gases, is in charge. It's not just drifting in the background, it's actively cooling the entire atmosphere. Pluto has flipped a long-standing assumption in planetary science, showing that under the right conditions, haze can dominate the climate system. But that wasn't the only discovery Webb made. With its ability to separate Pluto and Charon's thermal signatures for the first time, scientists were able to cleanly subtract Charon's contribution and isolate Pluto's haze emission with precision. In doing so, they confirmed another long-standing theory that Pluto is slowly leaking methane into space, and some of that methane is falling onto Charon. There on Charon's poles, the methane gets exposed to sunlight and cosmic radiation, triggering chemical reactions that produce reddish organic compounds. This explains the dark red caps seen at Charon's poles, first hinted at by New Horizons. This study reveals something far more profound than just solving a mystery about Pluto. Pluto might not be the only world where haze dominates atmospheric cooling. Other cold, distant worlds in our solar system, like Saturn's moon Titan or Neptune's moon Triton, also have nitrogen-rich atmospheres filled with haze. Until now, scientists assumed gases alone explained their temperatures, but this discovery forces us to reconsider. If haze is cooling Pluto, could it also be shaping the climates of these icy moons? Second, the implications stretch far beyond our solar system. Many exoplanets, especially those orbiting far from their stars or cloaked in hazy atmospheres, may not follow the rules we've long used to model climate and habitability. If particles like haze dominate their energy balance, our traditional gas-based models might miss the mark. We may need to rewrite how we assess whether distant worlds are stable, warm enough for life, or even habitable. And perhaps most intriguingly, this mechanism may echo back to Earth's own distant past. About 2.4 billion years ago, before the Great Oxygenation Event, Earth's atmosphere may have resembled Pluto's, rich in nitrogen and hydrocarbons, with thick hazes formed by ultraviolet light. These ancient hazes could have helped regulate temperature and driven complex chemistry, possibly playing a role in making early Earth suitable for life. What started as a mystery about Pluto's cold skies has turned into a story with cosmic significance, reshaping how we understand planets, moons, and even the origins of life itself. So thanks for watching, and thanks to Ground News for sponsoring this video. If you're tired of clickbait headlines and just want the real story, especially in science, scan this QR code or head to the link ground.news/SOU given in the description. You'll get 40% off the Vantage plan and finally see the news like you see the universe clearly.